The most distant human-made object in existence today is NASA's legendary Voyager 1 spacecraft. This remarkable piece of engineering has managed to accomplish what no other machine built by human hands ever has. It has ventured beyond the reaches of our solar system and entered interstellar space, a realm previously untouched by any Earthbound creation. Just imagine the audacity of launching a spacecraft over 45 years ago, during an era when computing power was primitive by today's standards. And yet, this spacecraft continues to explore regions of space that no one thought possible at the time of its conception. Even more astounding, it has long surpassed its original mission duration and capabilities, continuing to operate decades past its planned expiration. This is not just a technical feat. It's a symbol of human curiosity and scientific determination. It is the incredible reality of a bold NASA mission that is steadily redefining what we know about deep space exploration. Yet as incredible as its distance and longevity may be, there's something even more fascinating. Voyager 1, floating billions of miles away from its launch point on Earth, still sends signals and valuable scientific data back to our planet. And it does so using technology so outdated, it would be considered prehistoric by today's standards. Technology even older than the cassette player. The spacecraft's instruments and systems are a snapshot of late 1970s engineering. Still, despite the simplicity of its components by modern metrics, it performs with astonishing precision. That's not all. Voyager 1, launched in the summer of 1977, has recently made a groundbreaking discovery that has sent ripples throughout the global scientific community. This unexpected revelation has captivated researchers, space enthusiasts, and the public alike. The question now looms: what exactly did it find in the farthest corners of space? And perhaps more importantly, what does this finding mean for life here on Earth? To understand the magnitude of this achievement, we must return to a key moment in the history of space exploration, a moment that marked the dawn of the modern deep space era. During the early 1970s, a brilliant scientist named Gary Flandreau, working at NASA's Jet Propulsion Laboratory, made a groundbreaking observation. Using just a pencil, a calculator, and his sharp intellect, Flandreau discovered that the four gas giant planets, Jupiter, Saturn, Uranus, and Neptune, would soon align in a rare and favorable configuration. This alignment, which occurs only once every 176 years, presented a unique opportunity. By carefully timing a spacecraft's launch and trajectory, engineers could use the gravity of each planet to slingshot the spacecraft toward the next, dramatically increasing its speed and conserving fuel, a maneuver now known as gravitational assist or gravity slingshot. This planetary alignment would allow a spacecraft to travel from Earth to Neptune in just 12 years instead of the 30 years. Such a journey would typically require using conventional propulsion. This was an extraordinary opportunity, and NASA acted swiftly. In the summer of 1977, the agency launched two identical spacecraft, Voyager 1 and Voyager 2, just 15 days apart, in order to seize the fleeting cosmic alignment. At the time, no one could have predicted the profound legacy these twin explorers would establish. They were initially intended to conduct a 4-year mission to explore Jupiter and Saturn. However, what they ended up achieving was far beyond what even the most optimistic mission planners imagined. More than 45 years later, both Voyager 1 and Voyager 2 remain operational, defying the odds and expectations of longevity in space. They continue to send back streams of invaluable scientific data from the very edges of our solar system. These two spacecraft have traveled farther than any other object built by humanity, pushing the boundaries of known space. What's even more impressive is that their continued operations have outlived their creators' expectations by over 4 decades. Originally envisioned as simple planetary flybys, the Voyager probes evolved into full-fledged interstellar explorers. Their journeys have fundamentally changed our understanding of the outer solar system. From the very beginning, the Voyager spacecraft delivered astonishing results. As they passed by Jupiter and Saturn, they sent back breathtaking close-up images of these massive planets and their mysterious moons. They revealed active geological features that no one had anticipated: towering volcanoes on Jupiter's moon Io and icy terrains on Saturn's moon Enceladus that suggested internal heating and possibly subsurface oceans. These early discoveries reshaped scientific theories and opened new frontiers in planetary science. Voyager 2 went even further, becoming the first, and still only, spacecraft to fly by Uranus in 1986 and Neptune in 1989. It provided humanity's first detailed views of these ice giants, exposing complex magnetic fields, dynamic atmospheres, and unexpectedly varied moons. Today, the Voyager probes are more than 14 billion kilometers, or about 9 billion miles, from Earth. Each is roughly the size of a Volkswagen Beetle. Yet these relatively small spacecraft have delivered insights that rival the most ambitious missions ever attempted. They began their journeys by performing a gravity assist maneuver around Venus, an unprecedented feat at the time. Their course to Jupiter took them 10 times farther than Mercury is from Earth, requiring passage through the perilous asteroid belt, a region once feared as a graveyard for spacecraft. While the Pioneer 10 and 11 missions had previously navigated this region, Voyager did so with added complexity and ambition. Despite the daunting technical limitations, the spacecraft were marvels of their time. With only 69 kilobytes of memory, an amount minuscule by modern standards, their onboard computers had to autonomously manage operations and adapt to unknowns without real-time assistance from Earth. Data from the instruments was recorded on magnetic tape, then transmitted to Earth, using a 23-watt radio transmitter, the same power draw as a standard household light bulb. Their 12-foot-wide dish antennas enabled communication across billions of kilometers using radio waves traveling at the speed of light. But even light speed has its delays. As the spacecraft drifted farther from Earth, the time for a signal to reach mission control increased. Voyager 2's signals now take over 18 hours to reach Earth. Compounding the challenge, Earth's own radio noise from cell towers, TVs, and other technologies makes detecting Voyager's faint whispers ever more difficult. Nevertheless, the Voyager probes continue to defy all expectations. They have become the very embodiment of endurance and resilience, astonishing scientists with every passing year. Their journey has not only expanded the scope of our knowledge, but it has also changed how we understand the nature of space itself. As they continue into the void, they are heading toward the Oort cloud, a vast icy sphere of comet-like bodies surrounding the solar system and extending nearly halfway to the next nearest star. It will take the Voyagers tens of thousands of years to reach this region, but their entry into interstellar space has already begun. This transition occurred when the probes crossed the heliopause, the outer boundary where the sun's solar wind is no longer dominant and interstellar space begins. The heliopause was once estimated to lie about 50 astronomical units from Earth, but exact conditions at this boundary were largely theoretical. Despite this uncertainty, NASA continued to fund the mission, hoping to capture data from this historic crossing. When Voyager 1 finally crossed the heliopause on August 25, 2012, scientists expected to see significant changes, particularly in cosmic ray intensity and magnetic field orientation. What they found instead was both exciting and puzzling. While the spacecraft did detect a dramatic increase in plasma density, consistent with entry into interstellar space, it failed to observe the anticipated shift in the magnetic field's direction. This suggested that the magnetic fields of the heliosphere and the interstellar medium may be more aligned than previously thought, or perhaps that our understanding of the heliopause's structure needs refining. Voyager 1's data sparked debates and new theories, once again pushing science into uncharted territory. The Voyager mission continues to be a beacon of inspiration and exploration. In an age where attention spans are short and many projects are transient, the enduring relevance of these spacecraft reminds us of the value of patience, perseverance, and long-term vision in scientific inquiry. Let me know what you think in the comments box. If you enjoyed the video, don't forget to hit the like button and subscribe to the channel for more content that dives into the wonders of our universe.